it's one of those things that that a lot of folks think, why would we still use color tests if if we have all these instrumental techniques? They're so cheap. Yeah, I mean, it's just the Marquis reagent or the Levine test. You just have these vials and a spot plate, and you can put a little bit in there and test it and get a color change, and it can tell you really quickly. Another thing too that's important is these are portable, so they can go to the scene. And I'm really concerned so much now about not having a clandestine drug lab, but having a clandestine explosives lab. And so if you've got white powder, it may be an explosive, not a drug. And if you start scraping that, off into a bag or something for evidence, it might pop on you. Is it likely to cause a, complete explosion? Well, that's a risk, but you could lose your eye, or you could damage your hands or something like that. So some of these explosives are contact sensitive. I mean, you touch them and they pop or blow up. So there have been examples where they've had these explosives in capillary tubes, and they try to put them in a capillary tube, and then it detonates in the capillary tube, and then that's glass flying, so people could lose their eyesight. So there's a lot of dangers in the crime scene that these spot tests would go and help you confirm, okay, this is likely methamphetamine. But the fentanyl, some of their toxicity, and we'll talk about the fentalogs, just a few milligrams could be toxic, enough to kill you. So we've seen deaths of police officers just having a little bit of powder on them, and they wipe it off and it goes through their skin, and then I think some have died. I don't have a case that I could cite, but anecdotally, it's been very bad because it's such a strong opiate. It's like an elephant tranquilizer, so knocks you out. So here's the colorimetric drug analysis. We're going to go through this and focus on different color changes related to the drugs, and then we're going to look at the chemistry that goes behind these color changes. But first, let me just, for like public safety announcement, okay, this is a very dangerous situation if you see this. Like if you're at a bottle exchange, you go down to change out your propane for your grill, and you see a valve like this, don't ever take a tank like that. And in fact, you need to tell the person that's in charge that they need to call somebody to come and get that tank, because it's really dangerous. What that indicates is that this tank has not been used for propane, but has been used for anhydrous ammonia for making methamphetamine. And so this brass reacts with ammonia to produce this colored substance, the copper ammonium complex. And you can see that over there. The copper is a deep blue color in water. If you put ammonia around it, it's even deeper blue. Okay, and so this blue valve, this discolored valve that has all that blue residue on there, is showing that they've taken this propane tank, they've gone and stolen some anhydrous ammonia from like a farming operation. They use it to fertilize the soil. And so you can find anhydrous ammonia in rural areas. And people will hook up the hoses and transfer ammonia over to these propane tanks and then go use that in methamphetamine production. And so I put that in this set of notes since it's a color change. So if you see a discolored brass valve and it's blue, you need to tell somebody that's in charge of the situation that they need to take that tank out of service and to be very careful about it. Because if it still has ammonia in it and that valve busts off, then you're very high risk, because if you breathe in that ammonia, you'll get essentially chemical pneumonia. It'll get into your lungs and it'll turn basic, and then your body will try to dilute that strong base in your lungs, and your lungs will just fill up with liquid. So, and you'll cough yourself to death, really. So that's a dramatic situation, but that's again a color change that indicates something that's very dangerous. So, we could do this chemistry, we could do mass spec, we could do IR, all these different things. But we can see that these color changes are ancient. I mean, we've had things that change color since we've mixed things. Since the earliest humans had their little chemistry kits that they made up out of nature, and my 6-year-old self on the front porch. So we've been doing color changes, for a long time. And the functional groups, trying to classify the chemistry of these different substances sometimes can be really tricky, because the functional groups are complex. In organic, believe it or not, we took it easy on you. Like we pretty much gave you one functional group at a time. You know, oh, this is a carboxylic acid. Oh, this is an ester. But in real life, there's like 50 different functional groups on these molecules. So which one is it? Well, it's all of those. And so we can use these color change reactions as another form of classification of these drugs. We could classify them as acid, base, or neutral. So that's useful sometimes, and that'll tell you how the drug is absorbed in the body, whether it's the stomach or in the intestines. And then we can also focus on these different analytical methods, the color changes and so on. So we can look at the different drugs. There's a downloadable sort of flashcard sheet on Blackboard. Go ahead and pull that down and start looking at the different structures, and we'll see the drug structures today. Here we go. So we have acidic drugs, we have neutral drugs, we have different classifications about where they come from, like an alkaloid drug is as an extract of some sort of plant material. That's just again, not to make you think that you can just get one quick look at this and know them all, but I will point out the different functional groups. And so if we look at this, you know, we see carboxylic acid groups here. We see alcohol groups. We see basic groups like amines. And then we see neutral molecules that have these, you know, large fused ring structures. So you see this. Those fused ring structures really do create a lot of their bioactivity. So they get into those pockets and the different enzymes, and that's a lot of times what they're doing. So the shape of these ring structures is what causes this drug to do the things that it does. It fits into those pockets really well. And those you know, double bonds and so on interact with the amino acid residues in those various enzymes, and that's what makes these bioactive. We have some of these structures that are recognizable, though, more than just the functional groups. If you'll notice this piece right here, that tropane ring, it's a strange ring structure. You see that strange structure? That's going to be your indicator that that's cocaine related. And so this is actually a metabolite of cocaine. Over here is cocaine. It has that same structure. And so that's the level of recognition that I'd like you to have. If you're looking at these drugs, that you see that funky looking ring structure, that fused ring structure, you say, okay, that's a cocaine or cocaine metabolite. And then if you see this sort of four ring structure here, right there, see those four rings? That's going to be the opiates. Here's heroin over here. So this is morphine that I've circled, and here's heroin. See how it still has that same ring structure? So they're pretty easy to recognize. So at this point, I would like for you just to be able to recognize them, not draw them. I mean, I don't think I could draw any of these accurately. Like I would leave off a methyl group or an OH or something like that. But if I walked into the room and there was a talk going on and the screen showed that structure right there, I would know, oh, this is a talk on the opioids. Okay, and so I'll be able to recognize that. So that's what I would like for you guys to at least get up to that level where you see this structure on the screen, you say, okay, I know we're talking about opioids today. Okay. Some of these are, you know, not so easy to recognize, and so we'll stick with the main ones. Like if you see this 3-ring structure with a tail, that's one of your THC compounds. So cannabis, CBD, and so on. So that's those THC related compounds are going to be having similar shape to that molecule. You may have heard of GHB, gamma hydroxybutyrate, and that's a lot of times used in drug facilitated sexual assault because it's colorless, it's tasteless, it can be added to, it's water soluble, so it can be dropped in someone's drink, and it's, you know, like people, we had a talk, we had this alcohol and drug abuse summit where we would bring people in to talk about alcohol and drug abuse, and they would share their stories. And it was a young lady that shared a tragic story of her brother when they were in college ODing on GHB. And she described it as taking their inebriation, their partying to the next level, that they would put that in their drink, and it would be like in one little capful getting like 10 or 12 drinks. I mean, it would just be, you would be totally trashed. And so he, at the party, was crazy, and he took a swig of the bottle, and it just totally sedated him to where his lungs quit pumping, like his body just quit reacting to the lower brainstem, and so he died just because his brainstem was so sedated that it quit pumping the heart and quit making him breathe. Okay. They knew something was wrong, so he passed out. Well, drunk people pass out, right? But his lips turned blue, and so they were like, something's not right. And so he died. So she was so naturally traumatized by that she made it her mission to go on a speaking tour. There's like a campus speaking group, and she joined that speaking group, and they go around and send their speakers around to campuses and so on. The difficult thing about GHB is because it is so water soluble that you pee it out almost immediately, so it's really hard to detect. And so that's something that's, again, another public service announcement. If you ever were or suspected that you were a victim of GHB, you've got to get a sample of urine almost immediately, because after a couple of eliminations, you go to the bathroom 3 or 4 times, it's back down to natural levels. So you do have some of this molecule in your body, so you can't detect it at trace amounts, because trace amounts are in your body all the time. So once it comes down to background, there's no evidence left that it was a spike. Do you follow me? So it's, again, it's one of those really difficult drugs to detect. If you think it was a, like I said, if you or someone you know, you think there was a drug-facilitated sexual assault with GHB, they need to be able to collect urine. I mean, it sounds strange, but if there was ever a chance that would help somebody, I always try to mention it, because it is such a difficult molecule to detect, because your body naturally produces some. And so to catch a large amount would be tricky. This is a more common or more recent issue. This is fentanyl, which has similar effects as the opioids. Okay, in fact, it's being mixed in to some of the opioid formulations to make it more potent. And some of these are less expensive because they're common tranquilizers. And so what I would like to do for this, and you'll see down here, homework and test question, can you use the above figure to draw the structure of all these analogs named to the right? And so this is something you've probably not experienced, is this kind of chemical drawing. So when we talk about fentanyl, it's this version here. So the black structures can make up fentanyl. And so this is the base structure. And then you have R1, R2, and R3. And so for fentanyl, all of the black structures for R1, R2, and R3 make up fentanyl. So you would take this piece here, this R2 here, and put in this piece. So this piece would attach right there. And then R3 would be a hydrogen, so the hydrogen would attach there. And R1 would be this piece here, this ketone would attach at R1. And that would make up fentanyl. So it's like Tinker Toys. You take the base structure and you find the pieces that add up to the black structure, and you put those on there, and then that's fentanyl. And then if you were to make the green one, okay, so the green one, since we don't have any other R2 options, then we use this base fentanyl structure. So this goes on to R2, and this hydrogen goes on for R3. And then for the green acetylfentanyl, instead of this extra piece, we have just an acetyl group. And so this piece goes on to R1. So do you see how that works? So it's a base structure of fentanyl, and you only replace the pieces that you have to replace. And that's why they're called fentanyl analogs. So it's fentanyl base structure, and then you've removed R1 and put a different R1 on. Or removed R1 and R2 and put a different R1 and R2. And so you see how are you going to regulate this or put laws into place? So you fentanyl and its analogs. You would have to classify that, and then you would have to say which analogs. And so you'd have to put this into the law, because what if then they put a chlorine on there, instead of the R1, and that has some effect. And you've got to cover that with the law, because chloro is not in this one. And so somehow you've got to write the language that says fentanyl and its analogs so that they're all controlled substances, not just the ones that you list. Yes?
So on the test, would we get the entire top part and not like the color bar?
Yeah, so the point is, can you take that business up top and make these different analogs? Okay. Because I wanted you to know how to take that base structure with R1, R2, and R3 and understand how to replace the functional groups. And so we still use these color tests. They're easy for visual examination. You can take photographs and so on. Like we just saw a video, we could see what the test looks like, so it's easily transmitted to other folks. These are presumptive tests. A large majority of the labs still use them. These are the 4 ones that are listed by the bell text. So duocanolivine or cobalt thiocyanate, Marquis Reagent for opiates, and then PDMAB for LSD. So you would have these reagents in your lab. They're pretty simple. You can take the vial, you know, like she said, use the spatula. Sometimes there's not enough to use a spatula on. So you might think, how am I going to test this? There might be residue in this little pipe. You know, some high school kid says, that's just a decoration. You're like, really? Well, you can run methanol around inside that glassware and then drop the methanol onto the spot plate and the methanol will evaporate. And so then you've used methanol to extract out the surface of all of that glass and put it on the spot plate and let the methanol evaporate. And you may want to treat your standard the same way. So you may want to put a little standard in a different glass vial, put a drop of methanol in there, extract your standard to the glass plate so that it's treated exactly the same as your test object. And then you can do the spot test and you can do the confirmation tests. Okay. This takes advantage of one of the most sensitive detectors in nature. That's our eye. Okay, so we can tell, you know, like 50 micrograms pretty easily with our eye. So even maybe down to 1 microgram. And your accuracy improves with experience. So the more trained you are, the more times you've seen this test, there's slight changes in how it reacts over time. So you put the drop in there and you can see the color develop. And so that slowness and that behavior is something that you get used to. And so when something's not right, you know it. And so you can make in your notes, you can say this behaved a little differently. And then you test your standard and it behaves the same, so you can write those things down. Your eye and your human ability to write down your observations is key here in these spot tests. Thin layer chromatography, that's TLC. So it's easily adapted to TLC as a spot developer. So if you have a complex mixture, let's say you were saying, what if your field sample is not pure, which they're typically not, then you can use thin layer chromatography to separate your samples and then spray your reagent onto the TLC plate. And then you can also extract or do a TLC on your standard so that you see it move the same distance and it had the same color change. So you always want to treat your standard the same way you treat your field sample. And then you can have a negative TLC plate that you still run solvent on. Okay, and you spray the reagent onto it and you don't see any color change. And so you know that your negative control worked. Now, some of the things that we do spectroscopically, if the color gets stronger, we call that a hyperchromic shift. If it gets weaker, like it's a pale color and you're not exactly sure, you could put it, the terminology would be hypochromic. It's not as strong a color. If there's a red shift or a blue shift, that's where we get to bathochromic. Bathochromic is a red shift. You see wavelength increases to the right. And then hypsochromic is a blue shift. There's other ways to talk about these colorant compounds, and we use the word pigment and dye. There's really nothing chemically different about those. In other words, you can't say, this particular chemical structure is a pigment and that chemical structure is a dye. It just depends upon the carrier. So if the coloring molecule is insoluble in the matrix, then it's a pigment. So it's just suspended in that. And a lot of times our inks are pigments because carbon black isn't dissolving in the solution, it's just being suspended. And so you have a black ink pen, the carbon black is stabilized to stay dispersed in the solvent, but it's not dissolved. What's the difference between dispersed and dissolved? Well, think about the molecular level. So a pigment that's dispersed in the solvent is still little chunks, little clusters of molecules. But a truly soluble substance is molecularly dissolved. So individual molecules are dissolved in the solvent for a dye. But a pigment, you've got little particles of the pigment that are suspended in the solvent, and that's what we call it a pigment. So the difference really isn't that important for the spot test, but for ink analysis, it's important. So you might be able to get in there microscopically and see the clusters of pigment. So you can say, okay, this was a formulation that had the colorant molecule was a pigment instead of a dye. Now the different families of these colored molecules, dyes or pigments, are listed here. And so because it's used for classification, I'd like for you to at least be able to recognize these 4 different chemical structures or chemical ways of bonding things together. And so here they are. From the upper left, you have a triarylmethine. And these names are, you know, they should tell you something, right? You know what aryl means, right? Aromatic ring. So we have 1, 2, and 3. But where's the methine? What on earth is that? With the I there. Well, it's a methane. It's lost one of its partners. Okay, so carbon likes to bond to 2 things. Here, carbon's bonded to 3 things. And so it's triarylmethine. So you see that carbon in the middle it's not just having a hydrogen that's not listed, you know, like organic chemists are lazy and they leave off all the hydrogens. That's actually a carbon with 3, it's an sp2 carbon. So we have triarylmethine dyes, and that chromophore gives a peak in the visible spectrum, so it's colored. Now, how do you get the different colors out of this? The different functional groups around the outside. And so if they pull the electron density out into the rings, you have a bigger box, you have smaller spacing between the energy levels, just like the particle in the box in the fall that we talked about. And so you have a shift of the peak and you get a different color. It doesn't take much at all in the visible spectrum to shift from yellow to orange or from orange to red. Or the biggest one is yellow to green. It just takes a tiny little shift and you'll go from yellow to green, which is a huge change psychologically. You see that, you're like, this is yellow, that's green. Spectroscopically, tiny little shift. You look at those spectra and you say, these are almost the same. You look at the color of those spectra, they're completely different. So just one little change out here on the outskirts of this particular functional group will give you a drastically different color. Carbonyl dyes, you know, not all carbonyls are colored, but when you couple a carbonyl dye with this extended pi cloud, then you get a chromophore in the visible region. So you get some sort of color active agent. It just means it has a peak in the visible spectrum, and so it's going to be colored. You know, here we have a different extended pi cloud, larger molecule, and then you see those carbonyls on there. So this would be classified, these 2 would be classified as carbonyl dyes. That one on the top is indigo, so the deep blue substance. And this was anthraquinone, but I don't know what color that is. Then we have nitro dyes. And so these are nitro groups here. Now, you can get a colored substance by just putting 1 nitro on something. Like if you have nitrobenzene, it's no longer colorless, it's yellow. So the nitro groups by themselves will absorb like the high 300s, and kind of the tail of those peaks will get into 400 nanometers. Once it starts cutting out light at 400 nanometers, it's taking away blue. If you take away the blue, you're left with yellow. And so your eye interprets that spectrum as yellow if you cut away any of the 400 nanometer light. And so the nitro groups will definitely make things yellow, but you extend that pi cloud and that peak starts to move in the red direction. And so then you have this one, it's a naphthol yellow, what do you know? And so then this sulfonate group here, or sulfite, it's put there, it doesn't really have any effect on the color. And that's really why they're valuable. So you can put an SO3 group on these organic molecules and not change the color. And why would you want it there? Why would you put all these SO3 groups on there if it doesn't change the color?
Act as a surfactant.
You're on the right track, surfactant. But it's reaction with water, so it's soluble in water. So these are solubilizers. So if you make it charged, you make it more water soluble. And so even though we have sort of partial charges on the nitro groups, they're not fully charged. So they're not really that interactive with water. There's a little bit of hydrogen bonding that goes with nitro groups, but you put on a negatively charged acid group, and now all of a sudden you have something that's going to pull that into water. So all of our food coloring dyes have a lot of SO3 groups on them. And then lastly, we have the azo dyes. So we have a lot of nitrogens in this molecule. Okay, we have an ammonium nitrogen here, we have an amine there, we have a nitro there, but this is the azo linkage. And that's a really important linkage. And those non-bonded electrons, it's the N to pi star transition that allows that azo group to rotate. And the way this is drawn is really kind of not the favorable way. A lot of times they're trans. This is cis. Okay. And you notice this is going to create steric hindrance because these hydrogens, which the organic chemists always leave off, are going to be right on top of each other. Right? And so they're banging into each other. So that creates a problem. And so then if you got into the trans structure, then those would be far away. It wouldn't be a problem. The rhodamin dye works with this azo linkage, and also rhodopsin in your eye. So light hits that N to pi star transition, causes this nitrogen group to freely rotate, and then when it comes back down, it slams back into a planar structure. And that little kick is what your nerve cells are detecting. So light hits the N to pi star transition, creates a kick in that molecule, and that causes electrical signals to go back to the back of your brain and say, I saw something. So it's pretty amazing. This is very, very important azo linkage. It's my favorite. Okay. Yeah. And so now let's look at these different reagents for creating color changes. Now the chemistry just gets ridiculous. Okay, because these reagents, typically reagents make dimers out of the molecule. And so what's going on? You got a white powder, and it's got some aromatic rings in it, and you make a dimer. And so now you've made the box twice as big. What happens to the energy levels? They crash down, and all the differences in those energy levels are now smaller, which means they show up at longer wavelengths. So these molecules as individual molecules would absorb in the UV. But you couple them together, make a dimer, and now you've got something that absorbs in the visible. So that's where we're getting the color change. We go from the UV of a single molecule to the visible with a dimer. And that's not the way all of them work, but the ones that we show here, the Marquis reagent and the Levine test, Simon-All complex, these all dimerize. So here we have methamphetamine, or amphetamine, and here's methamphetamine. Here's the methyl part. Okay. And so we can take this Marquis reagent and we can react it, and this is the place where the Marquis reagent attacks, and that's the point of dimerization. And so once it reacts with the Marquis reagent, you see that same active carbon is here and here, and they've now been connected. Now this is almost a triarylmethine. It's just a diarylmethine, but it's the same kind of concept. So this is a little twist on the triarylmethynes. It's just diarylmethine. See, the methine has got the positive charge on it, and then the two aryl groups. So it's dimerized them, and now you have, because this is this carbon has an open valence, that electron cloud can delocalize and go over this whole area. And so that's the area that is now the chromophore in the visible spectrum, whereas earlier it was just a single aromatic ring and it was in the UV. So now we have a colored substance. And that's going to give you like an orange red to brown. So it's going to be reddish brown. And that's okay because that's cold medicine. If it's methamphetamine, it's going to be a brighter orange. And you say, oh, that's a controlled substance. So orange brown or red versus orange, kind of a judgment call. But if you have your control and you have methamphetamine as a control, you look, well, this is orange and that's more red. So, either inconclusive or negative. And it'd be your judgment call there to see if it was inconclusive or just negative. Yes.
So, like, whenever she was using, like, the standard in the lab before,
Yeah.
did they not, like, force you to, like, measure out the amount you're using so they know when stuff is missing? Or, like, is the...
There would, she just had it in a little vial. But since I haven't worked in the crime lab, but I have worked in the explosive lab, we measured out how much you took out and how much you put back and everything. It was a pretty rigorous accounting. So, you would weigh the container and then you would take your lab sample out and you would weigh the container again and you write those masses. So we knew how much was missing from the safe. Okay. And then if you had some left over, you only want to take as much as you need so that you don't have to put any back. Okay. But if they see that, you're taking a lot out. He did a spot test, but he took a gram. That's just ridiculous, So, so, if you're a suspect and they keep looking at the log and they're like, okay, the masses don't match, somebody's dry labbing this, then, it's going to be a problem. They'll figure it out is basically what's going to happen. They're going to figure it out if you're taking a gram when you need a milligram. So...
Would she just weigh the vial before and after?
So if you have a tear weight, like you might, when you build, like if you're going to set up the say if you received a shipment, you're going to put it in your containers in the safe, you're going to tear those, and that's going to be at the top of the log sheet. So the mass of the container is in the top of the log sheet. And then you can just weigh the container from then on, and you can do by difference, what's in there. So it's you want to make it as simple as possible because, if it's simple, people will do it. It's just human nature. But if you make it incredibly complex, then you're going to have a harder time getting people to follow the rules. And so just weighing the container and writing down the mass, that's simple enough. Everybody's going to do that. And if they can't do that, they need to get fired. Right?
Would humidity affect those containers?
It depends. Yeah. I mean, also you just want to see if it's if that would be a big enough effect. Right. So that might be a question that you would ask. Just have a empty container and dry it and see how much, change there was. Yeah. But also it's very hard to track milligrams, right? So if somebody's stealing, 20 milligrams at a time, that's going to be really hard to detect. Okay. And so just like it would be hard to detect somebody that steals $5 every once in a while. You're not going to, but people don't typically steal $5. If people are stealing, they're stealing $200, $300. This is a little off topic, but it's the same kind of thing. People who start doing that start doing it more and more and more until it becomes a detectable level. My wife's an accountant, and there was somebody who was borrowing like a couple of $100 from their company and then going to the casinos on the weekend and then trying to win and then put the money back on Monday, And so they were making deposits back and forth. And so, you're not guaranteed to make your money back. And so then they started taking more money because they had to make the money back. And the whole idea was, well, I'm going to pay them back once I hit it big. But yeah, casinos don't work that way. And so, all this money was missing, and it was a really pretty clever scheme. They had set up some account numbers at the bank. They opened 2 accounts instead of 1. And so the account numbers were just 1 digit off. And so they were making deposits into their own account, but had the same name and everything. It was pretty tricky. So that's forensic accounting. This is forensic chemistry. But the same kind of principle applies. Is the person wasn't stealing $5. That'd be really hard to detect. But $200 at a time. And so that's when it kind of got above the level where we could detect it or could be detected. Okay, here's the Marquis reagent reacting with morphine. And once again, it's a dimerization. This one's a little more involved. So here's morphine, and you got that fused ring structure, and you've got this open double bond here, and that's where the Marquis reaction takes place. And you see here's those double bonds now, and we've dimerized. So we've gone from a box that's this big, and this molecule is white. And if you look in the visible spectrum, it's got barely no peaks, and now we've dimerized it. So look how big the conjugated cloud is now. So we've spread out the electron cloud. All the peak energy levels are closer together, so the absorptions have moved to the red direction because they're closer together. And so this gives us that violet color. Okay. And then it's just showing different places where that carbocation or oxonium cation can move around. So this is going to be sensitive to these little functional groups down here. And the thing that makes, we'll learn this too, the thing that makes morphine different than heroin versus codeine and so on are these little OH groups. And so if you have different functional groups in those 4 places, then you're going to get a slightly different color. So you'll get a little different color for morphine than heroin, than codeine, and so on, but they'll all have some sort of color change with this reagent. Now here's dimethylamino-benzaldehyde, and it'll react with this LSD molecule. Now this is a crazy molecule, and here's another way they've sort of simplified the structure. So this is LSD, it has this indole group at the bottom, and they've just gotten tired of drawing the rest of the molecule. So they drew this wavy line, okay? And so that's what this wavy line indicates, right? See the wavy lines? Everywhere there's those wavy lines, the top part of that molecule has just been erased. Right. And again, it's a way to, how do you show chemistry with these huge molecules and not, lose the tree for the forest? Right? We want to focus on where the chemistry is happening, and yet we have all of this extra structure. And so, in fact, we don't necessarily see that in our organic books. They like to give you all the glory of the molecule. And biochem too. I don't know. Biochem punts and just uses squares and circles and things sometimes. Or a little Y and a little triangle or a diamond, like we saw in the ELISA test, right? Because forget it. I mean, the enzyme is ridiculous. And so this is at least somewhere in between. We've got some chemicals still shown. This molecule reacts here on that indole ring, and it will attach itself, and then it will continue to react and make another, react with another one. And so here we have our triarylmethine. So we have the 2 indole rings and this PDMAB, and there's that carbon, which only has 3 bonded agents there. And so we have this triarylmethine, and you can see. So it's quite a complicated structure at the end because we have 2 of those wavy lines, which means we have 2 of those top pieces on there. Yes?
What color is it here?
It doesn't say, does it? I don't know. I'd have to look that up. Yeah. So, someone pull your phone out and look at color. Ehrlich's test for LSD. What color is it? Yeah. Purple? Purple's kind of a weird color too because it's not, I don't know, it's not that different from brown. It seems like it is visually, but it doesn't take much for purple to turn into brown.
It goes from purple
To just dark, yeah. Yeah. And so then we have the Lieberman test with phenols and amines. And so here we have, again, what we're doing is, in this case, we're dimerizing. So we have these small molecules with aromatic rings, and we pair them together. And so then we have now this extended conjugation area. And so this is going to be extended conjugation with the carbonyl. So here's a reaction that's showing the carbonyl group. You can treat it in an acidic solution, it's red, then you put in a drop of sodium hydroxide and it turns blue. and becomes basic. So that's a nice one too, because that's a two-part test. You do the test, and then you have it in acidic media, and then you put a drop of sodium hydroxide and shift the pH, and now the color changes again. So those are great because you have two color changes. And then here's methamphetamine tested with the Simon test. So we could do two tests. We could use the Marquis reagent or this Simon test. And this creates, actually, the Simon test comes in and reacts with that amine group. So it's attacking this part of this amine and adding on this iron piece. So this is the colored piece here. So this is the blue Simon-Aw complex. So the methamphetamine is over here. It's reacted, and now it's got this piece attached to it. So this is attaching a metal color center. And so this is slightly different than the others. It's not a triaromethine or an azo or carbonyl. It's actually got a metal complex stuck on it. Yeah, what's up?
This test, would it false positive for cough?
It might, yeah. And so you would have to know what the risks are with the different tests. So. And then here's the Ducanol reagent for marijuana. And so marijuana is a plant. Okay, you're going to get buds, you're going to get leaves, you're going to get like gooey stuff that's moldy, and you're going to wonder, what is this? And so you're going to crunch it up, and well, it's true. It's been sitting in someone's backpack for 6 weeks, and so, it's no longer healthy plants. It's called green plant-like material, GPM, and so it may or may not be marijuana, okay? And so that's going to interfere with your test because it's this goopy stuff and fibrous. So what you do is you do an ether extract. So you crunch it up in a mortar and pestle, put some drops of ether in there, and then you can extract that. So the ether extract is what you start with. And then you add hydrochloric acid to make it acidic. And then you add chloroform to add an organic layer. And then the molecules move to the purple layer, or move to the organic layer, and they're purple. Okay, when you add the reagent. So you add the Ducanol reagent to dried petroleum ether extract. So you extract the material from plants or plant-like matter, and then you let it dry out so the ether evaporates, and then you add the Ducanol reagent, then you acidify it, then you add the organic layer. And they've taken THC, and then the Ducanol reagent has added this extra piece. And this is the chromophore for the Ducanol reagent. And you get a couple of different color changes depending upon the different components of THC. And so here we have, you can do this spot, you can take this, put it on a TLC plate and elute it, and then you can spray this fast blue reagent on there, and you can see the three different colors for THC, because there's three main compounds, the delta 3, delta 9, and the GPM. So this shows a nice little, wait, let's go back here. This one is just attached there. So this is really just an extended chromophore. It's not really one of the triaromethynes or anything, but this fast blue color change agent will take this this azide and will attack that fused ring structure. And notice this strange little setup they've got here. So here's your THC molecule. Let me find my mouse. This is THC, or one of those compounds. And here's an azo linkage for the fast blue chromophore. And notice the structure looks like it's attached to the middle of the ring. Why are they doing that? Any ideas? Yeah, it's ambiguous, right? It's saying it's attached to this ring somewhere. Okay. It doesn't mean that they don't know. It means that there may be a mixture of the two compounds. Like it could attach here, say 40% here and 60% there. Okay, and rather than saying that for sure, they just stick it to the middle of the ring and call it good. So this is what you're going to have to deal with, when you're trying to talk about structures. You've grown up in chemistry where everything is exactly precise. Think about organic. When they have a reaction that has branching, we've got 8% to this molecule, 12% to that molecule, and 70% to this molecule, and 10% to that. We've ironed out all of the questions. But you get into some of these applied areas of chemistry, and like environmental chemistry or forensic chemistry, and there's a lot of shortcuts used in the structures. Okay, so I just wanted to introduce some of these things to you. Not that you have to memorize all of these different reactions, but I'm trying to train you on how to understand the chemistry that's published. When you see something like this, what does that mean? That's what I'm really trying to teach you right here. And I'm teaching you to recognize an azodie versus a triarylmethine and so on. Or to recognize morphine or recognize methamphetamine. So do you see the different targets? If this were organic, I'd be teaching you the reaction and we'd be pushing electrons and everything like that. Okay? But if you're in an analytical lab analyzing drugs, you're not pushing electrons. Okay? But you are trying to communicate chemical structures. And so it's really important for you to understand what some person in a text or a paper means when they wrote that. Okay. Any questions on that?
So in court, would you have to defend this in any way? Like, would you have to give like a mini chem lecture and like?
I don't think so. I don't think they would ever get that detailed because you're not talking to any other chemists. Okay.
What is NIJ?
Yeah. If they tried to pull the thread on that, you would say this is irrelevant. This is the color structure, and this is what's giving us our color change, and it reacts with compounds in THC. And whether it attaches here or there is irrelevant, which is why we just showed it attached to that ring. Okay. That's right, but the thing is, you would definitely do your homework and make sure that there was no substantial color change if it was attached there or there, and that's going to be published somewhere. Okay. So you would pull the thread and make sure that doesn't, and then you would cite those papers in the court. And say, for those who have the background, you can pull these papers and you can see that there's no difference in the color change. That's probably the question. If they're going to challenge this, they're not challenging the organic chemistry. They're challenging whether their client is guilty or not. So it's the color change that's important. So they would look at that and say, you would have to pull those papers and say, here are the authors of this study, and they show the colors of these different compounds, and they're no different, or they're not significantly different, and this matched our standard, and the standard has the same ambiguity. So, what are we arguing about? It's not going to matter whether it was 65% and 35% on two different carbon atoms. Or it might. What if you discovered that it was, an issue? And so then you would, want to make sure you knew what you were talking about. But those, sometimes you have to maybe pull the thread. But in a court of law, you're not going to get into the pushing electrons and identifying which one is key unless it has a forensic impact, right? So then we did this color change. Since we're talking about color, let's just review this a little bit. Remember the color wheel? This was the freshman level colorimetry, where you have Roy G. Biv all the way around. And if it absorbs in the blue, it's going to be yellow. If it's absorbing in the yellow, it's probably going to be a violet color. The violet comes from having the light in the red and the blue. So your red and blue mix to make a purple color. So if you're absorbing in the yellow right in the middle, then your red and your blue get through. And so then you have that violet color. If it's really a huge peak in the yellow, then the tails of that peak start to absorb in the red and the blue. And so you have no yellow and very little red and blue. And so if you had no red and blue, no yellow, you'd have a black substance. If you have just a tiny amount of yellow and blue getting through, then you have a little bit of a purple color. Okay? So if you have just a little peak in the yellow and everything else is coming through, then you have a real pale pink purple color. So you can, look at this and say, all right, I know if I've got violet, I've got a peak somewhere in the yellow part of the spectrum. Then we wanted to get a little bit better. Instead of Roy G. Biv, now we have yellow. So here's red. So here's R. And then I don't really see much orange. They're calling that yellow-red. Here's yellow. Here's G for green. Here's blue. And here's, well, we'll say, probably right. Let's go right here. Purple. Okay. So here's the color wheel. Roy G. Biv. The indigo is a purple blue. But what they've done is they've added now individual ones, like 5 green yellow and 10 green yellow. 10 green, 5 blue green, 10 blue green. And so they've put all the individual ones. And this was kind of funny, you know, little kids, when you're raising little kids, there's certain little things that kids do that make you laugh all the way till you're an old person. You know? And my son's favorite color, whenever we asked him what his favorite color was bluish greenish. And I don't know where he heard the ish part, but that was his favorite color. And I would just laugh about that. So, yeah. So where is that? That's right here. This was Thomas's favorite color, I guess. It was some bluish greenish, but I don't know if it was the 10 bluish greenish or the 5 bluish greenish. Yeah. So there's some ambiguity even then. You know, we don't know. And so they have these numbers that associate with the hue that goes around the outside, and then you have the chroma. So like, is it like a gray version of that color or a very bright version of that color? And then how you know, bright is it? Is it close to white or black? So this is the 3 coordinate Munsell color system. Kind of a complicated diagram, but you have a black and white value, 0 to 10. You have a 0 to 10 in terms of color saturation or chroma, and then you have this wheel that gives you the hue. And so for codeine or aspirin, like you could do a powder, white powders here, and you could dissolve the codeine in chloroform and then put it on your spot plate, and you would get a 7.5 P24, okay? And so you would come around here, it would be a 7.5 P. So where's that? Here's 5, no, let's see, here's 5P and 10P. So it's right in the middle of these two colors. And then it's a 2-4, so it's probably pretty dark. It's 2 and then out 4. And so that would be your color chain. That would be your color for that substance. So if you had never seen it before, this would give you some kind of indication as to what color you'd expect. Okay. This is not as good as having a standard. Right, let's go get some codeine and actually test it too. But if I'm trying to tell you what the color is, I've got to have a system. And so this is a way to communicate those colors. Notice how aspirin would be drastically different. So aspirin's a 310 and 5R. So 5R is aspirin. So that's, you can tell the difference between codeine and aspirin just by the hue. And then it's a 310, so it'd be up, it's a little brighter color, and out 10. So it would look a lot like this, maybe a little darker than that. Like add a little black to that red, and then it might be that color for aspirin. So you could tell the difference between codeine and aspirin. Even if you didn't have a control, you could use the Munsell color system and say, yeah, this is likely codeine. Because if it were aspirin, it would be red.
So just double checking its hue, value, chroma is how it's listed.
Yes, yes. And I might have the value chroma reversed. We'll have to check that, yeah. No, that's saturation. I've seen HSV instead of HCV, so yeah, I think it might be hue chroma value. I think value is last. Now, advanced colorimetry, this is going back to the chemistry side of things. This was a paper that I did that, you know, y'all did the RGB lab, and that RGB lab was really the first half of the research I did on color. The second half is using Gaussian to model the colors. And so instead of taking the transmission spectra or the absorbance spectra from the lab, you can create an absorbance spectrum using Gaussian. And so these are the molecular orbitals involved in phenolphthalein and the colors that you get out of it. So I just want to show this just because I'm super proud of it. that these are the molecular orbitals that are connected in the phenolphthalein color change. And you can see that there's just a simple rotation that gives, this this dramatic color. This carbonyl group rotates. Now phenolphthalein it's a triaromethine. There's a carbon in the middle, and they've got 3 aromatic rings around it. And rotating that carbonyl gives us the color very close to the color of phenolphthalein. And so it's acid-base active. So this is the acid that you're titrating. So when you get to base, it pulls the proton off of that thing, and now it's free to rotate. And when it rotates, you get the color change. You get a dramatic purple color. So anyway, I was happy. It was great. And so let's do a quick Kahoot. CMET concepts. I'd like to go back in time and test you on the partitioning. So let's go put our partitioning hat on.